Hello everyone, and welcome for this fourth and final video on the OpenTelemac river flooding tutorial. In this video, I'm going to show you how we can visualize the results of the run we launched, and then we are going to check how we can make a proper initialization of the files. Finally, we'll write a hydrogram to simulate the flooding of the river. Starting off where we stopped last time, we are just done running the program. And as you can see at the end, you should get end of time loop. My work is done. This means that Telemac is done running the file. And here, if you look at the folder where you launched the study, you should get a new result file called r2d-evet.slf. This is a file we are now going to visualize with Salome. So first, let's exit the Docker container of OpenTelemac and run the Salome Docker container. To exit the Docker container, you can just type Ctrl-D. Now we are back in the WSL terminal. We can type the alias Salome and run the Salome Docker container. You can also just use the local version of Salome you have on your computer. Once you're inside Salome, go into the Paravis module, right-click in the pipeline browser and select Open. Then, select the r2d-evet.slf file, the results file, and press OK. You can then click on Apply, and we can see again the contour we draw on QGIS. If you want to see all of the mesh elements, you can replace surface visualization to surface with edges. This way you can really see the mesh elements. For now, we are going back to the surface representation, and we are going to represent the water depth variable. In red, you can see the water that I initialize on cats on video number 2. The time steps are here. And if you play the video, you can see the water is going to propagate. The water enters the mesh domain very fast at this boundary because we impose the water elevation, and this elevation is maybe a bit too high compared to the riverbed. On this side, we impose the flow rate profile of 2 meters squared per second, and this might be not enough because we see it's really initializing slowly. So now we are going to go back into the steering file and run again the simulation after adjusting some parameters to make sure we initialize properly the river. We are now going to put in the variables for graphic printouts the free surface. This is an S here. The free surface is going to be particularly useful for some post-process with filters on Paravis. We are also going to increase a little bit the flow rate profile we are imposing. Let's say we are putting 5 meters square second instead of 2. And we're not going to change the prescribed elevation here. 20,000 seconds is not enough, so we might put a bit more. Let's say we are going to put now 100,000. We don't have necessarily to change the time step. So now we can simply run again the simulation with this new set of parameters to really initialize a stationary state for the river. So let's exit Salome, and now we can run again the OpenTelemac container, and let's run again the simulation. We don't have to delete the results file, as if we generate another result file that has the same name, it's going to replace this one with rt2-evet old. So you can just run the simulation again like this by typing the same command than before. So now it's going to run, and I'll meet you once the simulation has converged. Now that the run has converged, you can see that we have two results files, r2t-evet, which is a new one, and r2t-evet old one, which was the first one we generated before. Let's open a new terminal and go into Salome. We go in the Paravis module and we open it exactly like we did before. You see now that the free surface has appeared among the physical fields that you can plot. Let's look again at the water depths first. There are 100 time steps that can be displayed because we raised the duration of the simulation, but we did not change the period for graphic output. Let's now play the animation. So we see that the right boundaries stop here because we simply imposed a constant water level, so even though the water propagates fast, at some point it does not move anymore. We see that at the end of this simulation, we still did not completely finish to initialize the river, as this part is still completely dry. Let's go back to the steering file. Now, in the previous computation file, instead of putting GeoEvet, let's put the results file. R2T event. This way, the computation will begin at the last time step and it will keep initializing the river. Let's now go back to the terminal with the OpenTelemac Docker container and let's run again this simulation. Now that the run converged, we see that once again, we have a new results file called R2D event, and then we have two old results files. Now, if we go back to the Docker container of Salome, we can again open the R2T event file the way we did before, but here it's already open, and you can right click on it and press reload files to actualize it. We do it. The first time step starts at the end of the previous computation. Now if you press play, we see that the river reaches a stationary state. We can rescale the color map. Let me now show you how we can apply some filter on this result to get a better view. Click on the result file and go in filter, then search and look for warp by scalar. Then select the bottom here and press apply. Now we see the actual relief of the mesh we defined in CAT. We can also exaggerate a little bit by putting a scale factor of 5 here. And we can change the color map by clicking on this button. And here select the following color map. We can also display the water in 3 dimensions using the free surface. So once again, go in filters, recent, warp by scalar. But now the scalar that we will use for the warp is going to be the free surface. Put a scale factor a little bit smaller than the one you used for the bottom. So here I put 5 for the bottom. I'm going to put 4.9999 for the free surface and press apply. Then let's change the color map of the water depth to the usual cool to warm color map. And as you can see here, we really see in 3 dimensions the water propagating. Now that we have a stationary state for the river, we are going to impose a flooding profile. To do that, let's go back in VS Code and let's create a new file. You can then save it as floodingprofile.csv. In this file, we are going to put the time and the value of the flow rate and water elevation on the liquid boundaries. In the first line, you need to declare all of the variables that you want to vary. So the first one is going to be the time. The second one is going to be the flow rate. And the third one is going to be the water elevation. Please note that when you're imposing a variable at a liquid boundary, you need to specify which is the number of the liquid boundary. Here, the flow rate was on the second liquid boundary. So we need to put here Q2 and SL1 to specify that this variable here, the second variable, is the flow rate of the second liquid boundary. And this one, SL is for water level, is going to be the water elevation of the first boundary. In the second line, you can specify the unit of all of these. So the first one is going to be the time in second. The second one is the flow rate in meter square per second. And the third one is the water elevation in meter. Now you can just give the value that the variables are going to take. So for instance, if we want to simulate flooding on 100,000 seconds, we are going to do here a 0, then maybe 10,000, 20,000, 40,000, 60,000, 80,000, and then we end up at 100k seconds. Note that the simulation you're running should end a little bit before the final value you're giving here for the time. Let's do the same for defining the associated flow rate. So at t equal to 0, we are in a stationary state. I'm going to impose a flow rate profile of 5 meters cubed per second. Then we want to make it a bit higher to start simulating a flooding. So let's put it, for instance, to 10. Then even higher, 20. Here, 30. Then it's going to be the peak here at 40. And then we are going to make it go down progressively from 20 to 5 again. We are not going to vary the water elevation, so we are simply going to let it to 60.5 all the time. Now we need to specify in the steering file that these are the values we are going to give as a function of time for the liquid boundaries. To do this, you need to add in the file section a new liquid boundary file keyword. And here you put the name of the file we just created. Finally, you can also comment the prescribed flow rates and prescribed elevation, as we don't need them anymore since the flow rates and elevation are given by this file we just defined. Again, if you have any doubt, feel free to check the reference file, and here you can see that the keyword is indeed liquid boundaries file. So now I correct here the boundary to boundaries, and Telemac should be able to read this keyword when I will run the simulation. We can finally add one last keyword here, initial time set to 0, so that if we are doing a restart, the first time step is going to be 0. And let's run again the simulation and check there are no error message. The code is now running, and I'll catch you whenever it's done. We can look at the result on ParaView again. And this time we do not have to reapply the filters, as we can simply reload the results file here. And now let's play the animation. We see that the water level is starting to rise at some places. For instance, if we compare this place at the beginning of the flooding and during the flooding, at, for instance, the 60 time step, you see that this place has much more water during the peak of the flooding. This way, you can use OpenTelemac to identify areas that are sensitive to flooding. Thank you for following this tutorial on the simulation of river flooding using the Telemac 2D module of OpenTelemac. I hope this video helped you to grasp the basic steps required in order to set up a study. Feel free to contact us, either in the comments, in a GitHub issue, or through our website. Let us know what topics you'd like us to cover next. In the meantime, don't forget to subscribe to stay updated with our future content. Goodbye!